Okay, so all data processing goes through this critical path of moving the data from the disk to the memory to the CPU cache. No matter the language, no matter the framework, no matter the tool, the data will move across these three components. And because this critical path is the common denominator of all data processing, it is important to optimize, to design around this data movement, to optimize for this data movement. And that is what this talk is about. Hi, everyone. I'm Kriti. I'm a database researcher at the University of Waterloo. Um, my research right now is developing the idea of eventual durability. I'm also affiliated with CWI Amsterdam, where I'm working on incremental view maintenance. I used to be a data engineer, which is how I got into database research. So, why is P99 important? It is important because at scale, the insignificant becomes significant. In the context of this talk, a single IO takes an insignificant amount of time. It happens like this. But when it is GBs of data and thousands of IO operations, these small latencies they add up and they become insignificant. There's also resource contention that happens because it's never the case that a single server is going to serve only one request. And that is why it is crucial to reduce these latencies wherever possible, optimize for these latencies. So today I'm going to be motivating. Today I'm going to be talking about this. I will first motivate the problem statement. I will talk about why it's important to design around this data movement, optimize for this data movement. I will discuss three existing techniques which do exactly that. I will talk about how they how they optimize this data movement. Finally, I will conclude this talk. It's going to be a short talk. So, this is an example I picked from MIT's lectures on performance engineering. It's a very good talk. It's available on YouTube, and I recommend everyone to watch it. It is the perfect demonstration of the how the latency, the data access latencies, inform the overall running time of an operation. Right. Matrix multiplication. There are two matrices which you multiply and obtain the third matrix. You multiply a row of A with a column of B to obtain this cell in C. Something to note here is that one row in A will be multiplied with every column in B. So B's columns will be iterated upon the number of times there are rows in A. So clearly, B will be accessed most of the time. And the way we access B, since B is getting accessed most of the time, the way we access B is going to inform the overall running time. Let's see how that happens. So this is the example of the case where B is getting accessed optimally. Everything, okay, so first of all, the data in the matrix data, it's stored in the memory row by row, in a row major order. So one row is stored, and then the next row, and then the next row. With this particular access pattern, anything that you need from any of these three matrices, they've already been brought into the CPU cache. So you don't have to go out to the memory and to bring it back in. And because of this, the running time is 3 minutes. Let's see an example where the access is not as optimal. This is the example where with this particular access pattern, whenever you need something in C or A, you've already brought it into your CPU caches. But with B, since the data is stored in a row major order, you bring in one row and to you use one value out of it, and then to access the next value, you go out to the memory and you bring it back in. And you have to do this every time B is getting accessed. So B is seeing a very bad access pattern, not an optimal access pattern at all. And which is why the running time of this particular access pattern becomes 20 minutes. So 3 minutes and 20 minutes. This code was written in C++, and that is why this is the access pattern. If you write it in Python, this is if you write it in Python, the running time goes is 10 minutes versus 6 hours. It is this drastic difference in running time, just that it is important that we think about the way our data is accessed, the way the data is brought in, is moved from one level to the other, and the way the data is laid out on storage. And the three techniques that I'm talking about today do exactly that. So the first technique is about how aggregate queries are processed in in a database. So this is the TPCH query one. What it's doing is it's taking a base table, doing some filtration on top of it, it's grouping the data, and then calculating a bunch of aggregates on it. Finally, it is returning the result ordered by your grouping columns. For the TPC at scale factor 1, the base table contains 6 million rows. After filtering, the actual aggregates operation is performed on 5 million rows. The 5 million rows are reduced to 4 rows. So the result of this operation is 4 rows. Since it's a grouping operation, no matter how big your base table is, it will be reduced to 4 rows. So with a TPCA scale factor 1000, your 5 billion rows is going to be reduced to 4 rows. Let's see how this happens in a standard database. So what a standard database does is it first of all sorts your entire data. So it takes your 5 million or 5 billion rows and it sorts that data. How does a database sort such huge amounts of data? It uses an external merge sort, which is a merge sort, but your disk comes into play. So it reads your data from the disk. It reads two sets of data from the disk, and then it starts merging them. As it merges and sorts them, it writes it to the disk. Because the data is huge, this involves a lot of read and write cycles. So you pull in data from the disk, you dump it to the disk, pull in from the disk, spill it to the disk. This happens again and again until your data is sorted. Finally, when your data is sorted, it is read as a single stream from the disk and aggregated and reduced into 4 rows. Something to note here is that as we are sorting the data, we are going out to the disk multiple times. Remember that, because that is the critical part that gets optimized. So this new technique, it says, don't sort the data. Let's not sort the data. What it says is, as you read the data from the disk, simultaneously create an index on on the values of your grouping column. So, and because this is an aggregate, your index will assimilate all of your data that you are reading from the disk. So, for example, you're reading from the disk and you're building the index. You encounter A and a corresponding value and its corresponding value. The next time you see you see this value and you put it in the index. The next time you see A, you say that, okay, A is already in the index, and you just add or average or increment the count that is already in your index. So, first of all, this reduces disk accesses because it has eliminated all the disk access that happens as you're sorting the data. Since this is a grouping query, it's an aggregate query, your this index is going to the result is going to be smaller than your the size of your original base table. And because of that, in most cases your result is going to fit into memory, and thereby it eliminates all the you don't have to go out to the disk again and again. Even if your index doesn't fit into memory, even if you have to spill your index out to the disk, because it's an aggregate, you're reducing the volume of the data. As you perform the aggregates, the number of disk accesses will be less than the number of disk accesses that you'll do if when you're sorting the data. Because with sorting, you're not reducing the volume of the data. The volume of the data remains the same until finally, when the data is sorted, you start reducing the data. So in that, you eliminate a lot of disk accesses. Obviously, if the cardinality of your grouping column is very high, then you might be doing a lot of disk accesses. But this is the whole idea of designing an algorithm so as to minimize your disk accesses. The next technique is also about how we can how we can optimize disk accesses. Most of us will be familiar with this vectorized query processing. So we most of us know that whenever the workloads are analytical in nature, you it is best to store data in a columnar fashion. Columnar fashion is you store all the values of one column altogether, then the values of the next column altogether, then the values of the next column altogether. This is as in contrast to the storing the data in a row major order, which is where you store values of a single row together, then the next row, then the next row. Let's see how this works in practice. So imagine an arbitrary query. The operator 1, operator 2, operator 3 are the relational operators present in the query. Here, the data is stored in the row major order. So you pull in one row, and you pick the value that your query needs to operate on, the relevant value, and push it through these operators till you generate the result. Then you bring in another row. Then you bring in another row. Uh, in this way, you're bringing in a lot of redundant data that you're not using. The IO, if when we store the data in a columnar fashion, we optimize IO bandwidth a lot. So in this case, the values of all the columns are stored together. Not only do we avoid bringing in redundant data, but we can also bring in a batch of values, and this batch is called vector. That's why it's called vectorized query processing. We change our operators to work on this batch of operators, and we send this batch of operators through our operator pipeline to get a result of four values in a single go. So think batching. So in this way, disk access is optimized, but this technique is also uh, CPU efficient, because let's see what happens in the first case. In the first case, you load the CPU registers with the instructions for operator 1. You load it with this single data point, and then it generates another result, and then you repeat it with the second data point, then you repeat it with the third data point, then you repeat it with the fourth data point. But in this case, you load your CPU register with the instructions of operator 1. You load the data registers with this vector, and you get the result for all four vectors. So you eliminate three extra CPU uh, reload cycles. Obviously, you cannot fit unlimited data into the CPU registers. So, but this alleviates the problem to an extent, and this is why it's CPU efficient. More can be done when it comes to CPU efficiency, which is what the next technique talks about: JIT query compilation, just in time query compilation. The idea behind JIT query compilation is that the code that actually runs to produce the result for a given query, generate that code at runtime. That is the idea behind JIT query compilation. Let's see how that works. So, in this case, what we are doing is we are taking a vector and pushing it through our operators. These operators are the relational operators present in your SQL query. Imagine, so for example, operator 1 can be a selection operator, operator 2 can be an aggregate operator, operator 3, just for the sake of argument, can be a join operator. It looks the actual join operator will look different. We'll have two inputs, but for the sake of argument, let operator 3 be a join operator. These operators are implemented as individual functions. So in your database code base, there'll be a function for selection, there'll be a function for aggregates, there'll be a function for joins, there'll be a function for projection. And when and it's a series of function, and between each operator there'll be a series of function calls. So uh, your so imagine your operator 1 has just produced data and it's just done. Now, to before operator 2 gets loaded and is set to execute, a series of function calls will happen. In this series of function calls, your CPU registers definitely get evicted. So the idea behind JIT query compilation is that can we is blurs the boundaries between these three operators. So instead of these three operators being three different functions, uh, it becomes a single function. So all the code that is required for a query to run is compiled into a single function. And so when this runs, you load this entire single function into your CPU registers, give it some data, and it produces an output without having to reload the CPU with the instructions for the next operator. And in this way, you get more out of your CPU. The catch here is that in this single function will look different for every query that you want to execute, because every query will look different. So instead of stitching your operators together, it will generate code for all the code for that query in a single function at runtime. So this the code base becomes complex because of the code gen that is happening, but ultimately uh, it's it's CPU efficient. And this is the underlying this is the catch, we can say, of all these techniques, that on one hand they give you performance, but on the other hand, your code becomes complex. So that is all I have for today. I have talked about this data movement across these different levels of disk, memory, and CPU. And I've tried to make a case for why it is important to design our systems, design our algorithms to optimize for this data movement, to get more out of our machines and our systems, to get a better performance. The catch in most cases is that your code becomes complex, more variance comes into play, because but it is worth it, given the performance that we want out of our systems, and given that we get more performance out of our machines. That's it for today. Thank you for tuning in.